All right, as we continue on with our study of earth science, we have now looked at rocks and minerals. Then we looked at the earth and plate tectonics and um, the hydrologic cycle and geologic time. And now we're going to talk about oceans. Now, oceans, obviously, the hydrologic cycle, we dealt a lot with water there, and oceans are a vast majority of the water on Earth. So, understanding those oceans is an important thing. So, diving in, now you might remember that 97% of all of the water on Earth is in oceans. 71% of the Earth's surface is covered by water. So, we usually see a map that looks like this here, or a globe, I should say, not a map, it's a globe. But we're only looking at roughly half of the Earth. And that half of the Earth has a lot of land mass. And we tend to think, well, there's a lot of mass. But if you turn to the other side of the Earth, and now if you look at the features, you see, look, right here is California. This is North America, or the west coast of the United States here. Up here is Alaska. So I've got blue on here is the United States. Blue, I should color this in while I'm at it. That's the United States. And then we have South America down, well, Mexico and Central America is actually what we see there. And then we have some Russia. We have Japan over here. And we come down, we have Australia and a few things. But it's mostly water over there. And so this side here, we might have 30% water, 30 to 40%, I'm just guessing. Or ocean, I should say. But over here, we have over 90% ocean on that side. So if we put it all together, we end up with 71% of the Earth's surface covered with water. Now, water is a very unique thing. Let's just review what we learned from physics and chemistry. Water has that H2O chemical formula. Oxygen is more electronegative than hydrogen, so the oxygen has a net minus 0.70 charge because it's pulling it's pulling the electrons more than hydrogen. Each hydrogen has a plus 0.35 charge because it is giving up about 35% of its electron. And so because of that, a water molecule will bond to another water molecule with the negative 0.70 of this oxygen having a bond to that plus 0.35 of the hydrogen. That's the dipole-dipole bond. And so that gives water a number of unique things. Things like when it forms a solid, it forms a crystal based on this that is actually more volume, less dense, so ice floats. But another important thing is the specific heat. If you put heat, remember heat is a flow of energy, into water, the amount of heat is equal to the mass times specific heat multiplied by change in temperature. So the temperature change, if C is large, C being the specific heat, then the temperature change will be small. So a result of this is all of these oceans, all this water on the surface of the Earth, you can pull a lot of heat out, and it only cools by a small amount. You can pump a lot of heat in, it only warms up by a small amount. So regions that are near the coast don't have nearly as big a temperature swings as regions that are inland. So if you compare, now I noticed in this map, we had Africa, Asia, Europe. We don't really have North America on this map. But over here we are. If you are on the west coast of the United States, you have the Pacific Ocean there, huge ocean you can see here. And that huge ocean brings cool water down. So we have cool water that comes down from the north. And so that cool water, it warms up as you come south, and it keeps the temperatures on land similar to the ocean temperatures. And it's already warmed up, so it's well above freezing by the time you get to California. So on the coast of California, you have virtually no freezing, but you also have virtually no 100-degree temperatures because of that high specific heat capacity of the water, which is very nice. Now, we've already talked about the Earth's atmospheres. We talked about the first atmosphere, the primary atmosphere, which was from the solar nebula, hydrogen and helium. And then we had the secondary atmosphere that was hot gases that escape through volcanoes and whatnot. And then we have comets brought water and other, quote, volatiles, and oxygen through the process of photosynthesis was put into the atmosphere. Hydrogen and other gases evaporated, carbon dioxide, well, hydrogen and helium were lost. Carbon dioxide was encapsulated in rocks. And we ended up with our current tertiary atmosphere that is about 79% nitrogen gas and 21% oxygen gas. And the water vapor condensing into oceans is really important for life on Earth. If you look at the planet Venus, Venus is a very hot planet. We'll learn that in our astronomy section coming up. And because it's so, well, it's believed that Venus never actually got cool enough for liquid water to form on its surface. It always had the water just in the atmosphere, but the water in the atmosphere is a very strong greenhouse gas. And so it just was never able to cool enough to have liquid water to be able to take the carbon dioxide then out of the atmosphere. So it has an atmosphere that's very high carbon dioxide content. It has very high, it has a runaway greenhouse effect, which makes it so it's very hot everywhere on that planet. Too much greenhouse effect, you can't live. On the other hand, if you look at Mars, Mars doesn't have any water on it. It doesn't have any atmosphere, hence it has virtually no, I say has no atmosphere. It has about 1/100th of the Earth's atmosphere. It has virtually no atmosphere, so it has virtually no greenhouse effect. And because it has no greenhouse effect, it's too cold to have a liquid water. And so, well, it gets too cold at night. It actually, the daytime temperatures on Mars would be around 60 to 70 Fahrenheit if the sun is shining on you. But as soon as the sun doesn't shine, you don't have atmosphere, you don't lock in heat, and it gets very cold. So our greenhouse effect caused by our atmosphere and the distribution of heat caused by the atmosphere as well as water are very important for us to even have life on Earth. Now we're looking at the ocean, so let's look at the ocean. So if we look at the ocean, you have different pieces of the ocean. So you have, and I'm going to start on the continent. So here you have continent, and then you have the coast. I love the coast. I grew up on the coast. You have the shoreline, and then you have continental shelf. You have not very deep ocean going out a ways. So that, what's inside my blue here, that's the continental shelf. And then you have, following the continental shelf, you have the continental slope. I know where I drew mine, and I guess I misread where this ends. It ends more like here. So the continental slope is where it's dropping down in depth. And then there's a continental rise where there's still a little more drop, and that's just because debris is accumulated. And then you have the not abysmal, but abyssal, like an abyss, the deep abyssal plain. That's the preponderance of your ocean floor. And then you have the mid-oceanic ridge here, which is where you have rifting. You have magma coming up from underneath, and that magma is making convection currents that pull these apart, pushing the ocean crust here so that it subducts. And then you have volcanoes and whatnot that are forming on that ridge. So that's the basic structure of the ocean floor. So you should know these things: the continental margin, the deep ocean basin, the ridge, the abyssal plain, continental slope. I'm not going to ask you about the continental rise, and the continental shelf. So you should know those terms, know what they are, why they're there, right? You have the actual separation between ocean and continental plates occurs here on the continental slope. And you can see here, these features here are caused by the compression of the ocean crust as it slides under. And so, of course, you have grinding that's going to make volcanoes come up there. So this is just describing the words that we had on the previous slide. So the continental shelf, the shallow extension of the continent that's underwater, and then the slope, the boundary between the continent and the ocean, and then the continental rise is just the wedge of sediment that's accumulated there. The ocean floor is different from the soil we walk on. The ocean floor is largely basalt. That's the magma that came up in the mid-ocean ridge here. That magma comes up and it cools quickly, so you don't have big crystals forming that basalt seafloor. And then you have a lot of sediment that builds up on top of that. The abyssal plains we've already talked about. Ocean trenches, not shown in this, but ocean trenches tend to be in this region here where you have the subduction occurring. And seamounts are volcanoes that occur on the ocean floor. And I'll have some pictures coming up of that. So here I have the ocean trenches spelled out more carefully. They're long, deep, steep troughs at subduction zones and seamounts, like I just said. The mid-ocean ridges where you have the spreading and lots of volcanic and tectonic activity there. And we have these ridges going all around the world in the midst of our oceans. So here are two different depth profiles for the ocean. So we have water level is 0 at the top, sea level. And you see the slope here is very clear. The rise, not so clear here between the slope and the rise now, is it? Abyssal plain here, nice flat region. Depth there is about 1 mile in depth. If we look here, though, we have the Tonga Trench. Remember, the trench is supposed to be where the two plates meet. So this is a little out from where the two plates meet, but you have caused by the subduction going here under the continental. But look at that depth. That's about twice the depth of the abyssal plain there in the upper picture. That's going from New England to Gibraltar, this one from Australia to the Andes. Then all of these little seamounts, little volcanoes underwater. Here is where you have the rise, where you have a rift. So that's moving that way and that's moving that way. And here is where you have the rift. So new ocean floors forming at these rises. And then you have another trench where you have subduction again of the ocean floor under the continental mass. And once again, now this isn't as deep as the Tonga Trench. Neither of these are as deep as the Marianas Trench. Okay, so now a question about that picture. Ocean trenches are the deepest part of the ocean floor. Why? Well, it comes to what makes it. It's made where subduction occurs. And so if you have this sliding under this, it's going to pull down. And so this ends up getting pulled down a little with it, making that trench. Now, this is a question, great, probably 15 years ago. I was in Southern California swimming in the ocean with one of my former students. He had been my TA for astronomy class and taking general physics from me. We're sitting there and looking at the waves, and he says, you know, I was out here with one of my friends, and he said, just imagine all those waves came from ships going out there in the sea. And then we just both started laughing. Ships are not what cause ocean waves. Well, what about motion of animals in the water? Nope. Currents running under the surface of the water. There are ships moving in the water, right? There are animals moving in the water. There are currents under the surface of the water, very important currents. We have a complex pattern of water currents that go from the Arctic down around the continents and wind their way back, and they distribute heat. They're really amazing. That's not what makes the waves. The sun and moon combine together to give us the tides. But tides are not waves. Tides is the average level of the ocean. The average level of the ocean moves up and down throughout the day, and that's because of the sun and moon. So what's left? It's wind blowing over the surface of the water. You might remember earlier we had a picture of how sand dunes were created. And we had air blows over, and it picks up stuff here, and then as it comes out here, it tumbles and it drops it off. That's basically the same action. It's not exactly the same, but you have the wind passing over the top lowers the pressure, so the water goes up in response to lower pressure. Remember we talked about the Bernoulli principle. And so the low pressure here, but then when it tumbles over here, you don't have that fast moving air, so you have higher pressure, it pushes it down. And so it's air blowing over water that makes the waves. Now, waves get their energy from the wind. The crest is the peak of the wave. So if I have a wave, well, let's not do that. Let's do it like this. This part here is the crest. The trough is the low part. So if you had another wave here, this would be the trough. The wave height is the distance between the trough and the crest. So this here, changed to red there. That there, I changed to red. That there is the height of the wave. And the wavelength is the horizontal distance between crests. So if I had another one here, this here would be the wavelength. Remember we use G in Greek, gamma, for the wavelength. And the period is the time between waves. So you might sit in the ocean and count the time between the waves, and it might be 2 seconds or something like that. That's the period of the waves. And all of these things are variables depending on the situation. So the height, length, and period of a wave depend on the wind speed, as well as the length of time the wind has been blowing and the distance over which the wind has been blowing. So if you have just a coastal breeze, you're not going to have nearly as much wave action as if you have a breeze that's going from Hawaii to California. So all of these things add up to give us the waves. And so you can look at this picture and see described the same things that I tried to describe before. One of the things that's interesting to note is the direction of the motion of the water. The water does circles as the wave passes. And as you go down, those circles get smaller and smaller. But the water's doing circles all the way down. So if you're out there in the ocean unsuspecting and a wave passes you by, you oftentimes get flipped over because the water is doing circles and you do too. Yeah, that's what I was just talking about. This is the one that talks about that motion. And the energy is being carried with the wave, not water. So the water that was at this part of the wave is not the same as the water here, but the energy gets transported. And you can have waves in deep water, and then when they come to shallow water, they change. So deep water waves, notice this, in shallow water, where the wavelength is about, or the depth is about 1/2 a wavelength, that's, if it's shallower than that, it's shallow water. It's deep water if the depth is more than 1/2 a wavelength. You might know something about tsunamis. Tsunamis have very long wavelengths. And because of those very long wavelengths, the entire ocean, mile deep ocean, is shallow water to those tsunamis. Just an interesting fact there. As the water gets shallower, the energy is still coming forward, but it can't be distributed through as much material. And so as a result, that energy builds up and you get taller and taller waves. So waves don't appear very big out in the middle of the ocean. But when they get to shore, they start to build up. So, you know, growing up around the beach, I love to sit there and watch the waves come in. And you see them out there and you see them just these little ripples. But then as they get closer, they start getting bigger. And then because of the friction of the ground stops the bottom part, and that's what causes them to break. Because the tops are still trying to move, but the bottom is being stopped by the ground. So that's why the waves build up at the shore. Something related to that, then, once again, if I talk about tsunamis, the tsunamis, as they travel through the ocean, the height of the waves is maybe an inch high. Not very tall at all for a tsunami traveling through the ocean. But when it gets to shallow water, suddenly they become very tall. That's why we have the word in Japanese tsunami, which means a harbor wave. They're waves that you don't see until they get to the harbor. Scientists really don't like to use the term tidal wave because it doesn't have anything to do with tides. Oh, and turbulent water created by the crash is called surf. Now, what happens when the water hits the shore? It all depends on energy and direction. Growing up at Monterey Bay Academy, when we had the storm surge would bring water farther upshore, and it would be very energetic, and it would pull away a lot of the sand. And so we would end up with our beach losing enormous amounts of sand, and there's these rocks that are under the beach, sandstone rocks as luck would have it, and those rocks would be exposed after big storms. So as kids, we'd go carve our name in it and whatnot. And then when we go back to normal, we have sand that comes brought in by the waves and deposited. Now, if the waves are coming straight in, they're not going to do as much erosion. But if they're coming at an angle, then the wave comes in and it's going to take sand like that, and it moves the sand along the shore. So the direction at which the waves are coming in makes a big difference for the erosion and deposition that's caused by the waves coming into the shore. So we get a lot of different shore type features. And so a cove is, well, a cove and a bay are basically the same thing. Those are places where the water has carved out, or maybe a stream has helped, a region that is kind of protected. So when water comes in, when waves come in, they actually bend in toward the shore because of the flattening of the surface. And in the cove, you're pretty much protected from waves. Then you have a headland, which is where you had some material that was hard to erode, and so it remained uneroded. So headlands and bays or coves. So here's pictures. This looks very similar to where we used to go for our grade school picnics. We have something that was pretty hard rock. So this was a headland at one time that came out like this. Erosion took away parts of it, so it eroded and made a hole through here that we call a sea arch. And here, obviously there used to be a sea arch there, but this is broken off, and so we have a sea stack. And then we have the cliffs, or bluff as I learned to call it. You can see here in this bottom picture, this is where I grew up. And we have this bluff, which, as you see on the page, is called the sea cliff as well. So we have the bluff, or sea cliff. There's actually a town close to where I grew up that was called Sea Cliff. And then, of course, you have the beach. Under here, we're going to have that continental shelf. And this picture, I'm sure, does not go out far enough to get to the continental rise. And those rocks I was talking about are actually buried right about there. Here's another picture just to give you some perspective. This here is part of the bluff here, looking out from sea level. And I know you don't care about any of these people, but yeah, these are all people that I knew once upon a time. And I was probably too young to be in this picture. That is, I was probably about 6. And what happened? Went all the way to the bottom. We were on slide 15, now we're on 40 something. Let me go to slide 15. Okay, I guess we weren't on 15, we were close. So just some more things about the beach. So what would we call this right here? If you said a headland, you are correct. And what would we call this here? We would call it a cove or a bay. And then we have some other features here. This clearly had water that was going sideways like that or the other way. And so it pulled sand along sideways, and we cut off a little piece here. That was a cove, but now it has water passing or soil passing in front of it, sand. And so that sand is called a barrier island. And then the lagoon is where the ocean was cut off by the barrier island. And a spit is where we have that sand that continued on, but it doesn't. If it doesn't make a cove, then it's not a barrier island, it's just a spit. And tidal inland is where the land comes in past the spit. So there's some more characteristics of the beach. Now, coral reefs are something completely different. Coral reefs are actively growing organisms. Coral is a growing organism, it's life. And those organisms secrete calcium carbonate, and that calcium carbonate, limestone, is what makes the coral reefs. So they're building, basically that coral reef is the house that these coral organisms grow as they go through life. And they, Moses says they survive on photosynthetic algae that are taking sunlight and using that for photosynthesis to get their energy. Coral bleaching, when it gets warmer, when water gets warmer, then the corals get bleached. They turn white, and it kills a lot of the coral. And that's an indicator of global warming. You don't have to have a thermometer. You can just look at the health of the coral reefs. So that's really one of the concerns with, the overall warming of our globe. What are we doing to these corals? Are we going to eliminate coral? It's a concern. Now tides. So we talked about waves. Now we're shifting to tides. Tides are caused by the gravitational attraction between, this shows the moon and the earth, and to a lesser extent the sun. And this goes back to our physics where we learned about the force of gravity is equal to gravitational constant, mass 1, mass 2, over the separation squared. So if I take from the center of the moon to here, that's going to be d for the near side of the earth. If I take from the center of the moon to here, I really should have changed colors on that. That's d for the far side of the earth. So if I take a little parcel of water that has a mass of 1 kilogram, and I calculate the force of the moon on that parcel of water, I'm dividing by a smaller number than if I took an equal parcel of water on the other side of the earth. So since I'm dividing by a smaller number here, the force of gravity on the near side is greater than the force of gravity on the far side, because it's proportional to 1 over the distance squared. So gravity is pulling the water closer to the moon harder than it's pulling the water that's farther. As a result, the water, it flows easily, elongates, so that we have a region on the side opposite the moon that is farther from the surface of the earth, and so that's a high tide. But simultaneously, the water that's closest to the moon is being pulled harder, and so it also has a high tide. So the water is a higher elevation on the side closest to the moon and the side farthest from the moon. And of course, if you look at the directions that are perpendicular, you have a low tide. And as the earth rotates, there would be low tides here as well. So the low tides are where you're at a 90-degree angle between the moon and the center of the earth and the ocean surface. So we have at any instant 2 high tides, one on the side facing the moon, one on the side opposite the moon. And since the earth is rotating, the locations of those high tides are also moving around the earth. So the earth spins on its axis once a day, and that's how we define a day. So you should have 2 distinct high tides 12 hours apart, except for one thing. The moon is also orbiting around the Earth. And so the moon takes around 29 days to do a complete orbit around the Earth. And so the actual time between high tides isn't 12 hours because of that rotation or orbit of the moon about the Earth. So high tides, it's not going to occur at noon every day. If the moon just stayed fixed, you could have that. Now, what about the sun? The sun also has distance near and distance far. And so the sun is also going to cause tidal effects. But because the difference between distance near and distance far as a proportion of the distance between the sun and the earth, or sun and the earth, because that proportion is small, the tidal effects of the sun are much less than of moon. But still, if you have an alignment where the moon is either between the earth and the sun, or the earth is between the moon and the sun, then the tidal effects of the moon and the earth are going to add together and give us the highest of high tides in this alignment, which we call spring tides. It doesn't have to do with the season spring, but spring tides occur when the sun, earth, and moon line up in a straight line so that the high tide caused by the sun and the high tide caused by the moon are at the same location. Now, if you rotated 90 degrees, now the moon is making its high tides here, but the sun is making its high tides here. They're in opposition to each other. Well, the moon is the stronger tidal effect because the proportion of the difference in distance is much bigger. And so this would be the high tide. This would still be a low tide. It's just not nearly as big of a difference. So this is the smallest high tide occurs in this geometry when it's a 90 degree angle between where someone on Earth sees the sun and the moon. And we call that a neap tide. Now there's one more important thing I want to talk about here. I don't have a slide for it, I was just checking. But the Earth rotates, right? So if we go back to this picture, if we go back to the picture here, the Earth is rotating. And so the Earth's rotation is going to be like this. And so the high tide is going to be pulled because of friction between the water and the ocean. Just like when I talked about the friction that makes the waves stack up when they get to the shore, that friction makes the water rotate with the Earth. Flat earthers sometimes say, why don't we feel the breeze if the Earth is actually rotating? Well, because just like the water, there's a friction that makes the air travel with the Earth. There's a friction that makes the water travel with the Earth, but that makes the high tides move. So in fact, if you have, here's the moon, and here's the Earth, with the Earth rotating like this, then the high tides are actually going to be pulled, and so I'm drawing my high tides as bars. They're going to be pulled forward, so they're not actually pointing at the moon. But as a result, the force on of the water pulling the moon is pulling the moon just a little forward. Here it'd be straight toward the Earth, and then it's got a little forward to it. And so the Earth's rotation and these high tides are dragging the moon forward. So they give the moon more energy over time. As the moon gets more energy, it goes faster. As it goes faster, it moves away from the Earth. So the moon is moving away from the Earth, I think it's about a ½ inch per year. Now, it's going to take a very, very long time for there to be any kind of noticeable difference. But the fact is, the moon is slowly moving away from the Earth because of the interaction between high tides and the moon. Okay, so that's talking about the ocean. Now let's talk a little about the atmosphere. The atmosphere, I said it was 79% nitrogen. This table says 78%. So sue me. So 78% nitrogen, 21% oxygen, 0.9% argon. So, you have, if you stop here, that's 99%. And then if you stop one level lower and include the argon, That's 99.9% of the Earth's atmosphere is nitrogen, oxygen, and argon. Vast preponderance of our atmosphere. Very small traces of these other things. Now, some of these other things are really important for global warming. Methane, water vapor, carbon dioxide, maybe a little of some of these others, but those are primary greenhouse gases there. They're very small components of our atmosphere. If they were big components, we'd be in trouble, right? But since they're small components, we have a livable, the required livable amount of greenhouse effect. Now, if we look at the Earth's atmosphere, the troposphere, that's where we have our weather. That's our low level. That's where we have clouds and we have rainstorms and whatnot. And if you go up above the troposphere, you have the stratosphere, which I tend to think of the stratosphere as the very high region, but it's higher than the troposphere. There's a very interesting thing going on when you look at temperature. So over here on the right-hand side, we have the temperature graph with altitude. And so if you start at the surface of the Earth and you go up, the temperature is getting much cooler as you go up. Hence, up here, I'm at 9,400 feet, which, 9,400 feet, that's, in kilometers. I haven't stopped to calculate how many kilometers that is, but it's probably around 3-ish kilometers. So I'm really down about here. Whereas in Lincoln, we're down about here. And so the temperature is going to be a fair amount cooler here than it is in Lincoln. When you get up to the top of the troposphere, you have the ozone layer. The ozone layer is absorbing a lot of radiation, breaks up the ozone as it absorbed. By the way, I just read an article this week about a massive hole in the ozone layer that's occurred in the Arctic. Scientists aren't worried about it at this point, but it's interesting that what causes that? Well, it's the ultraviolet light breaking down ozone, absorbing that energy and making it warmer up here. So the temperature starts to go up because you're absorbing radiation. But then you get up to the top of the stratosphere and you have the mesosphere, meso meaning metal, and it starts cooling down again. You get up to the very high portion, you have the thermosphere. Thermosphere, it starts to get really hot up there. But the air is, you're very far now from the Earth. So the air is so thin that even though it's very hot, it would feel cold to you because you'd have so few collisions between the air and your body. Now, in this, I didn't talk about the ionosphere. The ionosphere is a region where you have ionized air. That ionized air is something like if you're a ham radio operator, you use the skip off of the ionosphere so you can talk to people around the Earth, but that's not shown on here. The ionosphere is actually a region that includes part of the thermosphere and the exosphere. So the ionosphere is there. So let's talk about these in detail. The troposphere, that's where we have our weather. It's the lowest and thinnest layer. At the equator, it's 16 kilometers tall. At the poles, it's only 8 kilometers tall. So here where we are, we might expect it to be somewhere midway between there, maybe around 12 kilometers above the surface of the Earth is where you have that troposphere. It says thinnest layer. It's thinnest as in from top to bottom, not thinnest in terms of density of air, because it's the most dense air. So 90% of the atmosphere's mass is in that troposphere. It's the densest, thinnest from top to bottom. But densest. And so that's where we have clouds and fog and whatnot. And the temperature decreases by about 6 degrees Celsius per kilometer. So my estimate is I'm about maybe 3 kilometers above Lincoln. And so the temperature here, Hartzell, should be approximately 18 degrees Celsius cooler than Lincoln. Now, it's not. 18 degrees Celsius cooler would be somewhere around 35 degrees Fahrenheit cooler, and it's not that much cooler. Why? Well, because we do have a land mass here. It's not just air. The top of the troposphere is around minus 50 degrees Celsius. It's real stinking cold there. Then we get to that stratosphere. The top of the stratosphere is 50 kilometers above the surface. So it goes from around 8 to 16 kilometers up to 50 kilometers. And I should point out, the top of the troposphere actually depends on weather conditions. It can go up and down based on weather conditions. Within the stratosphere, we have that ozone layer that absorbs the harmful UV and causes warming once you get up there to the stratosphere. So it's minus 50 degrees Celsius at the base, but gets up to 0 degrees Celsius at the top, 32 Fahrenheit. So it warms up the stratosphere. Then we have the mesosphere, the middle region, extends from the stratosphere. Remember, that was about 50 kilometers to 80 kilometers. So it's about 30 kilometers thick, about the same thickness actually as you had for the stratosphere. And the temperature is going to once again decrease. Oh, please come back. Decrease again once you get to the mesosphere. So they have what they call a thermal pause, where you change from heating to cooling or cooling to heating, that is used to delineate where these occur. And there's very little absorption of light in here. That's why it's cooling. So it gets down to minus 90 degrees at the top of the mesosphere. And then the thermosphere temperature increases again, getting up to 1,500 degrees Celsius. Stinking hot. But there's very little gas out there. And final two things, the ionosphere, the electrified region within the thermosphere and upper mesosphere. So if we look back, thermosphere and upper mesosphere, the ionosphere is around here. And that's where you have, it says sprites, that's where you have northern lights. I'll change color. I hit. They occur there in the ionosphere. And what are auroras? Auroras are the northern lights and the southern lights. So northern lights are called aurora borealis, boreal meaning north. Southern lights are called aurora australis, for south. Then finally we have the exosphere. The exosphere is basically, okay, we've gone past almost all of the atmosphere. The rest of this is just a few atoms and molecules. And that's where atoms and molecules are going to escape. They're not going to be bound. Now, the sun is really important to our weather. And so solar radiation is the most important thing. Solar radiation is how much energy we receive from the sun. Most of our solar radiation is invisible, but there's also some short wavelength, what we call ultraviolet, or UV for short. So the UV radiation, that is radiation that is shorter wavelengths than blue light. Now, the Earth also emits radiation, and remember when we talked about the greenhouse effect, the Earth's radiation is infrared, or as we often say, IR, and that's a longer wavelength radiation. So we don't see the infrared radiation. We don't see the ultraviolet, but we see that visible. So we see light coming in because it has a strong visible component. We don't see the heat in infrared radiation that's going out. Now, solar intensity depends on, number one, how much radiation the sun is giving off. The sun will sometimes give off more radiation, sometimes less. But it also depends on the angle. So if the sun is directly overhead, then you're going to get all of that sunlight concentrated in a small region. But if it's on the horizon, that same sunlight is going to be spread over a much bigger area, which means that the energy received per second by a person standing there is much less. So in the evening and morning when the sun is on the horizon, you're not receiving as much sunlight per unit area, so you're not going to feel as much warming if you stand out in the sunlight. Whereas at midday, you have the maximal amount of sunlight per unit area. So if you're laying down, your whole body is going to be heated up much better at midday. So now I said midday, but keep in mind, here's the Earth. It's rotating about an axis like this. The sun is a big old ball out here. So the sunlight's coming in like this. And depending on the season, you're going to have more direct or less direct sunlight. So we are about here. So we go around like this. So sometimes the sun is hitting us at an angle like this. And as we go about, other times of the year, the Earth will be tilted like this. And now we're like this. And here the sunlight is almost directly overhead. Now, the fact is, we are at about 40 degrees north latitude, and the sun will only hit up to about 23.5 degrees north latitude. So we're always going to be a little north. But when we're tipped like this, which we call the summer solstice, then we're going to get the closest to directly overhead sunlight at noon. Here, what we call the winter solstice, we're going to get the most glancing sunlight, the least warming. And that's what makes the seasons. The summer solstice comes around June 22. June 22. And so around June 22, we're getting the most direct sunlight. And so we're getting the most heating. Doesn't make June 22 the hottest day of the year, though, because getting the most heating means the temperature is going to be rising the most each day. But you're still going to have the temperature rising after the summer solstice for a period of time, for about a month or so, because you're still receiving much more than average sunlight per day. But then when you get to, and we'll learn about these in the astronomy section, but when you get to the equinox, so the next equinox is going to be the autumnal equinox, you're going to be starting the autumn. You get to the winter solstice, you're receiving the least solar radiation. It's not the coldest, once again. December 22 is the winter solstice. That's not the coldest day of the year usually. The coldest day of the year usually is in mid to late January, because the Earth is cooling off. It's receiving less radiation than it's emitting, and so it continues to cool throughout the days after that. So the seasons are actually caused by the Earth's tilt. The Earth is tilted about 23.5 degrees. Oh, boy, you cannot read that. I'm going to do it here. The Earth is tilted about 23.5 degrees for its axis of rotation compared to the axis it orbits around the sun. And so that 23.5 degree tilt is the reason we have seasons. So here is a picture describing what I said. We have the Earth with its tilt going around the sun. So here we have the winter solstice. Places in the southern hemisphere are getting direct sunlight. Places in the northern hemisphere are getting glancing sunlight. Here we are at the equinox, and you have, just depending on your latitude, what angle it's going to be, but it's the most uniform radiation across the Earth. And then we have the summer solstice, when places in the northern hemisphere are getting, well, it's right on that line actually, direct sunlight, and the southern hemisphere, they're getting very glancing sunlight. Now, we actually describe the tropics as this region between where the sun is overhead. So if you live in the tropics, that means sometime during the year, the sun will be directly overhead. Okay, we will stop here and pick up next class period. Have a great day.